Welcome, folks. Thank you for joining on this Friday evening, afternoon. This is the Lockheed Martin Maryland Robotics Center seminar series. I would like to thank Lockheed Martin for their continued support of the seminar series. We are still in the virtual format, but hopefully next semester we might have some in-person presence. Let's just hope for the best. It's my distinct pleasure to be introducing our seminar speaker today, Dr. Josh Vander. Josh and I go back almost exactly 10 years now, when we were PhD students together at the University of Minnesota. And about 10 years back, right now, we were probably scrambling together to get our robotic system that's supposed to find and track radio-tagged fish in Minnesota lakes, working for an IROS paper submission. That was 10 years back. Josh now has moved on to robots that operate far beyond Minnesota lakes. He's a computer scientist, NIAC fellow, and technical group advisor at NASA Jet Propulsion Lab. He works on exploration, science, and defect projects there. His group, the AI Observation Planning and Analysis Group, is responsible for designing and deploying autonomous planning, sequencing, and scheduling to NASA instruments, robots, and spacecraft. Members of this group manage and contribute to deep ocean and under ice robotic explorers, the ISS, Earth Observing, OCO3, Mars Perseverance, Curiosity rovers, Europa Clipper, Psyche asteroid mission, and a bunch of other DoD missions. So I'm very excited to have Josh speak in our seminar series, and very excited to see what he has to say about the cool AI work that they are doing at NASA JPL. So Josh, take it away.
Sure, thank you, Pratap. So as he said, my name is Josh Vander. There are several artificial intelligence focused groups at JPL. So I have inherited half of one of them, and it became the Artificial Intelligence Observation Planning Analysis Group. We have about 14 members, and I took over that part of the group this year. So I'm a relatively new technical group supervisor. So this presentation will focus on what AI brings to JPL and also some of my own personal research. This is a picture of JPL. I think that this is the building that I will be in when we return to lab. So just so you know. Okay, advanced slides. There we go. I'm going to post these slides online if you would like to see them, and they'll be available at my website here. You just go to publications to find them. The first thing that you have to do when you talk about artificial intelligence is to define it, because it's such a broad and fairly nebulous field. And so the first part of this talk will be us discussing an example of what exactly it is and what exactly it does for JPL. You can find a lot of information about this particular application at this website here, which is our group's website. All right, so the example that I would like to present is for the Rosetta mission. And Rosetta was this really cool orbiter, which rendezvoused with a comet and dropped that little lander. You saw the drop animation, that was pretty cool. Onto the comet, and they got wonderful pictures. I'm borrowing these slides from Steve Chen, who is the other group supervisor in my section, focused on artificial intelligence, and he's kind of the godfather of AI at JPL. I hope nobody minds me saying that. And he would say, when presenting these slides, that this is a very large group effort. So it's not him, it's not any individual, it's a collaboration from many institutions and many people. You can see some of them listed here. And the final thing I'll say is that you can see him talk about this particular mission at length at this link here. And I do recommend you watch that. It's a very good talk. Okay, so at JPL, the first thing you must do when talking about any technology is justify its existence with respect to science. And so the first thing I will do is talk about why we sent a robot to a comet. So comets are very interesting, basically balls of ice and other material. They originate from two places, I think. One is the Kuiper Belt, and one is the Oort cloud, although I'm not very sure about that because I'm not an expert in comets. The Kuiper belt is sort of this flat disk out there by Pluto, and in fact, from my understanding, when Pluto was demoted away from being a planet, it actually just sort of joined its friends that it had more in common with in the Kuiper belt. So it's a Kuiper belt object. Outside of the Kuiper belt, extending very, very far, is this spherical shell called the Oort cloud. And it actually extends, I've learned, about 30% to the nearest star. So it's a huge structure. The reason that we would like to study these things is that they probably contained the building blocks of the solar system before it was the solar system. So as the solar system went through this process of contracting and collapsing and spinning and forming planets, all of these things were aggregated together and changed significantly. So we'd like to see what it looked like before. Rosetta was a very interesting mission to operate. I didn't take part in this, but I've learned. This is the comet trajectory, this purple ellipse. This other ellipse, this gold ellipse, I believe should be Jupiter. And then this red one should be Mars. And in here is Earth. And the white trajectory is actually Rosetta's trajectory. You can see it was launched and it did all these gravity assists and spin inside the inner solar system. And then after 10 years of operation, it finally arrived at the comet, rendezvoused with it. On the top right, you see these magnificent animations. These are actual pictures of the comet after the rendezvous. Again, I'll just plug this talk here by Steve Chen if you want to see more of this. Speaking of magnificent pictures, here is on the left, a series of pictures taken over half of an hour, showing zoomed in views of the comet from the spacecraft. And what you're seeing here is a very large cliff structure. You're seeing that the other part of the comet rotate into view in the background. You're seeing sort of dust fly in front of the camera. That's because comets are pretty active when they get near the sun, ejecting dust and such. And then this stuff that looks like snow falling in the background is actually stars rotating around as the imager on board the spacecraft tracks during its orbit and during the rotation of the comet. On the right, you will see a selfie. And actually, this is, I think, one of the first selfies attainable. It's very difficult to point a camera in a direction that captures the spacecraft because they normally don't want to do that. But you can also see the comet in the background. And apparently this was a 1 in a million shot to get both the spacecraft and the comet. Quite beautiful stuff. I really love looking at these pictures. Okay, so what is Rosetta? Rosetta is this box with some solar panels and a whole bunch of instruments in it. The instruments, what's important to know about this mission and all other missions that go far, far away into the solar system is that they are a collaboration of many different institutions, many different science teams, and many different engineering teams. So each of these instruments here has a different institution that wrote a proposal to build that instrument because it can measure something very important to the science team. So we're talking dozens of people, if not hundreds, involved in the creation and operation of each of these instruments on board the spacecraft. So you'll want to keep that in mind as we talk about how we actually operate the spacecraft and where AI can help us do that. The images that I've been showing, I believe, were taken by this OSIRIS instrument, which is an image. So when you're talking about operating a spacecraft like Rosetta, one thing that you should know is that, like I said, it takes a huge team and that AI is a very small part of this. This is sort of something you learn, or at least I have learned when I went into the real world, is that all the cool algorithms and all the neat research and all the really cool fancy stuff that you might write a paper about as a point technology tends to be a very small component of a very large moving system. And that's sort of what we're trying to say on this slide, right? Like there's teams all over the place in Madrid and Spain. There's all the uplink operations have a small part of that is planning and a small part of that is AI. This is fairly common, I've noticed, across projects at JPL and even across projects for defense. Okay, so let's talk about how technically challenging it is to actually plan the observations for this spacecraft. So on the left, you're going to see some of the constraints listed. Steve Chen, I think, would say, or maybe has said, that operating a spacecraft is basically a giant multi-objective optimization problem where you don't actually have access to the objective function. If people could say, I would be 3 happies if you got this observation, but 5 happies if you got that observation, that would be really nice. We'd plug those as coefficients to some optimization problem and just be done with it. But what ends up happening is that you have to take all of these constraints, the angle of reflection of the sunlight towards the observer, where the material is being objected from the target, the rotation of the target over time, the changing position of the observer, the changing position of the Earth, and so on, into account for each instrument. And then you have to satisfy each instrument operations team to make sure they're getting the data that they want. And so piecing all of that together to determine where to point the instruments and what instrument should be turned on at any particular time is an extremely challenging optimization problem. And like I said, we don't know when we're doing a good job except to show it to the teams and have them get angry at us, not us, these teams. So just as an example, one thing that you might want to measure is the outgassing that happens around a comet. So you might see some material coming off. And for that, you would want to be pointed somewhat near the sun, but not directly at the sun. You would want to have that material passing between you and the sun so that you can get the reflection, the refraction off of it. But again, you don't want to be pointed directly at the sun. This is a bad way to measure the side of the comet that we can actually see over here, the illuminated side. So during different times of the mission and different orbits, we have to turn on different instruments essentially. Oh, by the way, each of these observations has a side effect on the spacecraft itself. We have to rotate the spacecraft, we have to burn energy, we have to, I don't know, saturate reaction wheels and so on. We have to accumulate data in data storage. We have to eventually downlink that data storage as it fills up, which means to transmit it to Earth. So all of these have to be taken into account when determining a plan, which is why it's such a complicated process to operate a spacecraft, especially for a human team located across different institutions. This is an example of one of the plans that can be generated by an AI system that is responsible for solving this problem. So you'll see each row here is an instrument or a resource on board the spacecraft. And then the x-axis, sort of left to right, is time. And then these little blocks are times when that thing is active or possible. So you can see there's a downlink row here, and these are all the downlink perhaps opportunities. And then here you can see, anyway, all of these resources have blocks in which it's possible to use them or preferable to use them. And you have to sort of stitch together a timeline of activities. This is an example of a consumable resource. So this is the onboard data storage. And so you can do automated downlink scheduling. You can see that they're filling up as you take observations, and then they're dropping off as you do downlink or transfer to a different buffer or something else. Here's an example of what the AI system may generate as an observation plan, which would then be reviewed using tools like this by human operators before being uplinked to the spacecraft. So what you're seeing is a simulation of sort of running out that plan and showing what it would do and where it would take measurements. On the left, you can see the relative geometry. What I want you to see, I'll play this again here, assuming I can. Yep. What I want you to watch on the right is that we're scanning. So we're taking these little transect images or transect scans. And then in the middle of the scan, it's going to stop, point directly at the center of the comet for a second, and then go back. So what you're seeing is the AI system saying, now would be a good time to take this other unrelated measurement because we're pointed in the right direction, it's got the right illumination angle, and so on. And so it slots in that observation in the middle of these transect scans, which are being set up to serve another instrument's needs. So just beating the point to death, this is again the closed loop planning timeline. And I believe this was on a particular day at 20 January. So there's these MTPs, these are medium-term plans, short-term plans, and long-term plans. The Aspen tool is the AI tool that was developed by Steve Chen's group for this mission, or possibly for a prior mission, sorry. And what it did is it helped iterate between long-term plans and current trajectories, if I understood this correctly. But essentially the stage went, let's look at the previous medium-term plans, which are about a month long each. And let's do the data analysis and what we've downlinked to determine if we need to do more observations or more activities in the next medium-term plans. Then let's iterate on, this was for medium-term plan 13. And the way you would schedule medium-term plan 13 is to iterate on possible plans using an AI tool, which can quickly generate output activity timelines, which can then be reviewed. And if you don't like it, you go back to the engineers, you go back to the AI team, and you say, tweak this a little bit, introduce this constraint, change this a little bit. And this allows the medium-term planners to iterate back and forth with the possible trajectory and possible timelines to determine what it is that they wanted to do in the next actual medium-term plan. So the AI system essentially helped them to discover good plans based on all of these very difficult constraints and soft preferences that were in people's heads. Like I said, if they could specify this problem on paper, we could solve it easily, but it's really about iteration and discovery and learning as assisted by a planner. This is just one project. There are many, many projects. You can look at these 3 pages to find information about the other AI groups at JPL. These projects that I've listed here are just from this first website, which is the one that the one that contains our work. And again, I've just talked about Rosetta. There's another very interesting thing here that I would hope that would encourage you to go look at these projects. This is the Volcano Sensor Web. So the fun story about this is that there is this volcano that started erupting, and a volcanologist who was studying that volcano said, you know, I'd really like orbital imagery to see, I don't know, I guess the extent of the lava flows. So there happened to have been this mission up, Earth Absorbing 1, EO1, and he called a colleague at JPL who was on the EO1 team, if I remember correctly, and said, hey, can you please get some images of these lava flows? Well, it turns out that the team at JPL, working in collaboration with other missions, had set up this tiny little AI subsystem that was pulling in data from various sources, in situ assets or other observers, and saying, hey, does this remind me of something that we would have scheduled EO1 to observe, right? Does this seem to be an interrupting volcano? And if it is, can we just get EO1 to take that observation unprompted during a time when it's not doing something else? That actually worked. So the volcanologist had called JPL asking for an observation to be taken, and it had already been taken the night before because the system had detected and responded to that event in real time. Another example of how artificial intelligence can help the science missions by reacting quickly to things that are emerging. So in summary, this might be a good place to pause for a couple of minutes, but what does AI mean at JPL? Well, AI is really software tools that help us manage very complex systems or do processing of very complex sensor data or react very quickly to real world events. And it requires rigorous software engineering, right? So we're talking about existing real world systems and people and processes that we need to interact with. And at the very core of it is essentially algorithm or combinatorial analysis, which is the key breakthrough that allows people to do this quickly and efficiently. So maybe we can pause here and Pratap can help me walk through some questions if there are any.
Yeah, I had a couple of quick questions. So you mentioned so this closed loop where you generate plans and then I suppose it's humans who evaluate them and then you iterate over them. So do these use simulations? So what kind of tools do they use underneath in order for humans to evaluate them?
Right. So sometimes they just look at the timelines and they say, it doesn't make sense to do these at the same time, or I'd like to do these other 2 things at the same time. But often from my understanding, they do play it out in simulation to actually see what it's going to do, look at the trajectory, because there's just too many moving factors. So you need to see things. I would imagine it's a lot of plots and graphs and resource, plotting out geometry to see what your instrument geometry looks like. For the rovers, you can observe rover planning shifts at JPL when you work there. For the rovers, it's a combination of those things. So I imagine it's similar for other projects.
Okay. The question by John Lathrop, in the volcano imaging project, was there any human intervention in enabling the mission to image the volcano, or was it entirely autonomous from the recognition to the actual imaging?
I can't answer that specifically. There were always humans observing. It may have been as simple as a human pressing, I agree with this, but I actually don't know specifically. But the information's there on the website and in the papers, so we can both go check it out after this.
Awesome. All right. I think that's it for now.
Okay, so let's go on. All right, so now that you kind of understand what AI does at JPL, I want to spend some time presenting some of the current projects that are being supported by my group and other groups. Essentially, they're just orbiter and robotic systems for planetary exploration, and I've grouped them by the planet that we're trying to explore. So starting with Europa. So if you don't know, this is a picture of Europa. And Europa is actually quite a fascinating place. So it's farther away than Earth, it's by Jupiter. And that would mean normally that it's too cold to support life. Now, unfortunately, for that theory, it does seem to be able to potentially to support life. And there's a couple of things that you can see on this image that might hint that it's an interesting place to visit. So the first thing is there aren't a lot of craters. And if you look at our moon, it's got craters all over the place. That means that something is happening to change the surface and to erase those craters over time. And in fact, if you stare at it long enough, you see these brown streaks change over time, these little lenticulae change over time. That tells us that it's sort of a living planet. That's very interesting. And it turns out that Europa is much more interesting than just having a morphing surface. It actually seems to have a liquid saltwater subsurface ocean. So over here is Earth, and just sort of cartoony, this is the amount of water on Earth. This is the theorized amount of water on Europa. So it's a massive ocean. And the reason that surface is changing so much is because it's ice. It seems to be ice that is frozen on top of this ocean, and it's morphing and changing and crunching and expanding and all of that over time as the planet flexes or changes due to the gravity influence of Jupiter or due to just potentially other effects on the rocky seafloor. So why is this really interesting? Well, when we look at these dark, salty, cold oceans on Earth, we find life. And we sometimes find it clustered around these little hydrothermal vents. And so one of the theories of what might be going on under the ice in Europa is these hydrothermal vents are there causing heating and separation of the ice and so on. And that would be a great place to look for life. So I would just say that that was my attempt to inspire you to go to Europa, but you should go look at Kevin Ann's talk here. He does a much better job. He's an astrobiologist at JPL. So there is a current mission being built to go to Europa. It's on the right picture there. It's called Europa Clipper. And you can see Jupiter sort of ominously lingering in the background here. And the reason that Jupiter is working against us here is that it's a huge source of radiation, which can fry the electronics in these missions. So you can't linger too close to Jupiter very long. And so they've got this crazy, I guess, principled but very interesting series of orbits to actually dive into, rendezvous with Europa, get some images, loop back out to where it's safe, and then to continue that process. So they're just doing this spiraling pattern where they zoom in and get some images and zoom back out, more than images, but you understand. This is targeted to launch in 2024. Members of my group support the flight software and instrument software on board this mission. Farther out from 2024, what we'd really like to do is get through the ice and get into that ocean and start sampling around. So members of my group are working on these sort of high-level notional ocean worlds concepts. So we're developing technology which can support this mission if it actually does turn out to be feasible. The thing that we're working on here is building long-term autonomy so that this thing can find its way back to the base station, can find interesting things and investigate them. As I mentioned, one of the interesting things that we'd like to find on Europa is any hydrothermal vent or life that might be near the hydrothermal vents. So the best way to do that, at least from current understanding, is actually to find these plumes. So the plumes carry up a lot of the chemicals from the surrounding area up into areas where it can be found much more easily because it spreads it over such a large area. So if you can send in a submarine, then it can actually do these transects until it finds a plume, and then maybe find the center of the plume or find the source. Then you can do some very interesting science experiments. And so we're developing some autonomy, some adaptive sampling path planning. This work is led by Andrew Branch that can do these adaptive resolution or adaptive spacing grids to, in an energy efficient way, find the source of the plume and sample the interesting parts of that plume. This is fairly high TRL, technology readiness. We've done some field demonstrations with Naval Research Lab, Monterey Bay Aquarium Research Institute, and so on. Okay, so let's talk about Earth. Earth is another ocean world. We know that life exists on Earth. Earth has a lot of very interesting science going on. For example, what you're seeing here is a simulation, a model of the carbon dioxide circulation on Earth. And you can see a lot of very interesting sources, big cities, and so on. These pulses that are most visible here in the southern American continent or in Africa are the day-night cycle. And then these circulation patterns, of course, are the weather that we're familiar with. This is just a simulation, but this is what is used to inform our understanding of the future of the planet's climate. And to be confident in these simulations, we really need to measure specific points on the planet to determine if those simulations are predicting accurately or update the simulations and the models behind them. So one mission we support that does that is called OCO3. OCO3 is currently on the ISS. So this is the ISS. This is a submodule of the ISS, I believe, managed by Japan. And OCO3 is down here at the very bottom of that box. Is a pan tilt camera, essentially, although it's much more sophisticated than a camera. And again, I'll plug this link here where you can see from the operator's and designer's mouth exactly what OCO3 is doing. But essentially, OCO3 being a pan tilt camera, it allows you, as you fly over interesting parts of the world, to pan left or right to get these transects of measurements from parts either where you haven't measured before and you would like to now, or you can concentrate these transects in areas that are very interesting where you need more information about. This is on the left, a schedule of observations as output by the planner or a series of observations over time. Again, this is a challenging constraint satisfaction problem. So you've got a bunch of desired places you would like to view. You've got a fixed trajectory from the ISS, and you would like to know what's the long-term plan, what's the short-term plan, what are the pan tilt angles for the camera, when does it got to be turned on, and so on. This is a classic scheduling problem. So this is one of the things that the group is working on with the mission planning team to actually help them iterate just like they did with Rosetta, from my understanding. One of the other consequences of the CO2 buildup in the atmosphere is predicted to be a sea level rise. And one of the predominant sources of sea level rise, of course, is ice melt. And it turns out there's a lot of ice in the Arctic and Antarctic. And one of the things that's happening is this ice melt seems to be accelerating, and that's very scary. But we don't know how much it's accelerating very well. You can see the IPCC report on the right has some uncertainty in the actual global sea level trajectory. The reason for that is that there are these regions, for example, in Antarctica, where it's melting quite rapidly, but there are glaciers and other things holding back a lot of the bulk of the ice from hitting those rapid melting points. So you can see that, yeah. And so what we would like to know is, are these spots that are actually sort of holding back the rapid melt breaking down over time? Is this accelerating? Is it stable? We don't know. So there's been some missions to study this already. So we're just continuing this effort. One of the ways you can study this is you can actually launch some floats, hope that they float up underneath the ice, and you can get good measurements of salinity or of temperature, which would help you to understand if it's freshwater melt or if it's seawater going in. And they did this, and they dropped some floats. After a few months, they were able to pick up a few of them here. And after almost a year, one of them actually reappeared up in the north here, and they were able to pick it up and get the data. It's a fairly uncontrolled experiment, but we would like to be a little more principled about it. We do understand how the currents move under the ice to a certain extent through the use of models and understanding the seafloor geometry and the under ice geometry. So the project that is happening in my group is to understand how we can exploit this knowledge to actually come up with a system that can navigate for over a year under the ice. The concept's called Ice Node. This is led by Evan Clark. The way it works is similar. You drop a bunch of these things down. They have variable buoyancy, so they float down to these warm water currents, which are coming up underneath the ice. And then they jettison some ballast, anchor themselves on the underside of the ice, measure this flow rates coming off of the melting area. After a while, they release, float back out, and transmit the data home. This would, if it works, capture data about this very important area here, the grounding zone. The grounding zone is so important because there's this chimney effect. This warm water comes in, starts hitting the ice, melts it, and then moves back out. The more water exfiltrated on the top, the more warm water you're going to have coming in on the bottom, and you're going to have this positive feedback loop. So a couple of planning studies here, and this is ongoing work. So we've got some papers that are emerging on this. One of the things you can do is release them in an uncontrolled policy. So just release the buoys, don't exploit any knowledge. This is a good baseline study. 38% of them, if you release enough, will actually hit the grounding zone. The rest of them float off in this direction or get lost over here or end up shoaled somewhere else. We can look at the policy that was used by the previous mission, which was a fixed depth fractional policy. So float a certain amount off the seafloor, assuming you know where you are. And that actually does pretty good. It's about 64%. We'll reach this grounding zone and be able to stay there and get measurements. But actually, if you have uncertain knowledge of your transitions throughout this time, which would be what you would have from having a pretty good but not great circulation model, then you can actually formulate a Markov decision process and use MDP solutions to determine the policy of depths. So here we have an active depth controlled vehicle, which can, based on its current location, choose the appropriate depth to try to ride the current to the grounding zone or back out at the end of the mission. This seems to work really well, actually. We got 96% reaching the goal region. So that's cool. So this project, so I'm going to skip back a little bit. This project is being developed. It's largely a hardware effort, but like I said before, at the very center of that huge amount of software and hardware development is a little bit of AI, which makes it possible. Okay, so let's talk about Mars. Mars is in the news. It's very exciting. If you have not watched the video where these images came from, you are doing yourself a disservice, I believe. You can find it here. Please watch the landing video. It's very cool. We did not work on this phase of the Mars mission, but you should still watch it. One of the cool things that happened during the landing was terrain relative navigation. We didn't work on this either, but it is cool, and it is artificial intelligence at JPL. So the lander, as it's coming down, is actually looking down at the ground, finding features on the ground, comparing it to maps that it might have, and determining if it's in a safe area or not. And if it's not, it'll divert, and it'll land somewhere more safe. You can see this actually. So if you poke around Twitter or poke around JPL's website, you'll find an image of the hazard map of the crater, and you'll see that the lander managed to direct to a safe spot in the middle of a bunch of hazards and set down the rover. So it did a good job. We didn't work on this, but JPL did. Something we did do is to help the rover understand its environment, choose safe paths, and other things. We'll talk about the other things in a second. This is a real website, though. You can look at the Kelly Blue Book page for the Mars Perseverance rover. I think it's a joke, but they do hint at some self-driving software, which would allow the rover to make more independent decisions about how to cross obstacles and reduce the need for direct inputs from an earthbound driver. Stay tuned. This will be interesting if you see this. Something we can show is the onboard energy work that we did for the MSL and Mars 2020 rover. So you can check out some papers here or some publications and other project sites. Basically, all planetary rovers are energy bound. And so what you can do here is you can harvest the time left over from activities that have finished early. You plan new activities, or you can do the same for energy. You can start activities earlier or later, or move them around or reshuffle them to conserve energy. So one of the things you can do with those harvested resources is actually do extra science experiments. So here, we don't have time to communicate with the Earth, or Earth doesn't have time to react to the fact that those resources are available, but an onboard AI system can actually start to poke around and see what it can find. This has actually been done on MSL, and I would expect similar things to be done on Mars 2020. A lot of these people here are in my section. This is the paper. If you want to learn more about this, please go look at it. But essentially, the onboard camera for MSL could look at the rocks, compare what it's seeing in these images to parameters that are set up by scientists on the Earth, look for pancake rocks, look for highly textured rocks, and so on. And then it can actually do the ChemCam experiment, which, if I remember correctly, involves a little laser to puff out some vapor from these rocks, and then a spectrometer to actually look at it and get spectral information about how the rock is, or what the rock is composed of. I could be wrong, but the paper's here if you want to find out what it really does. But here's an image of it actually classifying the rocks into various different potential targets. And these are actually some of the ChemCam experiments being executed. The cool thing here is you can see that, consistent with our charter, we're using artificial intelligence to increase the amount of scientific data that can be gathered. Here's where this system was deployed. After deployment, 327 of these ChemCam shots were averaged per sol, which is execution cycle or Mars day, and prior 256. So you're getting a whole bunch more science data just by letting the system make a few more decisions. Okay, so let's talk about a couple of emerging concepts real quick. So this is one concept that I find very interesting, and it's called Mosaic, and it involves an intelligent constellation of orbiters. So one of the class of things that artificial intelligence can help you with is to observe things that a human operator could not react to. They happen too quickly. On Mars, these things do tend to happen more frequently than you might expect. One of them, very interesting one of them, is dust devils. So dust devils form pretty rapidly and pretty commonly over the surface of Mars. They tell us a lot about how the atmosphere works and how dust is transported into the atmosphere. And so we would like to observe them forming, observe their paths, and see what we can learn from that. So the concept for this study was, well, if you've got a constellation of small orbiters which are looking at the ground, and they queue, similar to the Volcano Sensor Net, can they queue each other for follow-up observations, or can they queue a high-resolution imager to get these high-resolution images of dust devils? Another thing you might want to observe on Mars is crater formations. So like any body in the solar system, things smash into it periodically. And on Mars, when this happens, and the craters that form and reveal the subsurface minerals, they can reveal ice, or they can just tell us a lot about the composition of the surface. So it's very interesting to observe these craters shortly after they have been formed, and hopefully a few more times at longer timescales until they start to look like the dead craters that are all over Mars. You can find more about cratering events here, but essentially one of the studies we did was to show how over time, if you have that constellation looking down at the ground always, with an imager always on, and if that imager can actually pick out a crater from an image, then what you'll do is you'll be able to count up hundreds of crater observations over the course of Martian years. So you're seeing here, x-axis is time, y-axis is the number of craters observed. And if you cut a slice horizontally here for any one of these observed craters, all of the dots correspond to the many different observations by the many different members of the constellation. So you can see we're observing tons of craters over time, and those craters are being observed multiple times over time. This is a very cool thing. All you have to do, fly a constellation with imagers and a little onboard planning. This is all just a concept. No one has agreed to do this yet. Here's a picture of a dust devil. This is a very large dust devil. In fact, you can see it's probably 50 meters, 100 meters across at the base, and it goes very high up into the atmosphere. We actually have a lot of these images because we've been looking at Mars for a long time from Mars Reconnaissance Orbiter and other orbiters around Mars. So this suggests that we may actually be able to, as I've alluded to, train a classifier to do detection on board a spacecraft. So there are people working on this. We tagged up with them to study how well this would work in terms of planning and scheduling, these observations. So this is just an example of correctly finding dust devils from imagery that was previously gathered that we have available on the ground. There's a couple false negatives here. This was actually a dust devil. And you can see that these parts of the crater or these ridge lines do look a little bit like dust devils. So you can understand how the classifier may have mistaken them. But it's okay to have these false positives because the goal is to find images of the evolution of dust devils over time. So if we get a few things that are not dust devils, that's actually not the end of the world if the majority of them are what we're looking for. So what we did is we studied, well, given this orbiter configuration, and the likely occurrence of dust devils over time, how many would you actually be able to observe? So this animation is showing the constellation moving. We had someone plan these orbits so that they observe at noon local time. And they're in a chain. You can see one after the other. This is helpful because the first one, when it detects a dust devil, can actually say, hey, I found one at these locations. Please schedule a follow-up observation. And in fact, since these things are moving, you may have to schedule a couple of follow-up observations so you can get it correctly centered or something else. So doing these studies, what you find is that you can get a whole bunch of dust devil observations per Martian, per mission. In fact, if you just look down at the ground, so that train of orbiters is just staring at its feet, sort of, then you're going to get about 114 of the 163 simulated events just randomly flow through your camera. Without doing any adjustment, you get, just as a baseline, about 13 follow-on observations. If you do some onboard scheduling, which is fairly realistic, so this means that we actually simulate the exchange of information, the timing constraints, motion, and all that, you can triple that number to get up to 33. So again, deploying a little bit of AI gets you a lot more science. What's interesting here, though, is there's a trade-off. We're not observing as many of the unique events. This is, of course, this should be intuitively obvious. It's the exploration versus exploitation trade-offs. How good could we possibly do? Well, if you take all of the events and you have an oracle on board that can tell you exactly where all the events are, the best that constellation could do is 55. That means that we are very close to best possible. This is all pending. You should see this in AAS soon enough. Okay, so I think that basically wraps up everything that I wanted to say. So I do want to say that JPL is a very diverse place. We've got people of all backgrounds, all walks of life. The fact that I work there tells you that there's all kinds of backgrounds. We support a huge variety of projects: defense, science, exploration of the Earth, exploration of the solar system. And AI at JPL tends to be what you might think of as computer science. It involves a lot of software engineering, combinatorial optimization, AI, algorithm design and analysis. And machine learning is not required to work in the AI that I've discussed here, but there are other groups that focus more on machine learning or processing sensor data. A top secret and SCI clearance is helpful for some of the projects. Like I said, we work on some defense projects. So that's just a note there. If you want to work at JPL, this is a helpful thing. These are the group websites here that you should go check out: AI, ML, and DUS, and JPL NASA Gov. And then this is my website where you can find these slides. So I will stop there. Thank you very much.
Thanks, Josh. I'm going to clap on behalf of everyone. Folks, we can open it up now for questions. So if you want, you can type the questions up, or you can raise your hand and I can unmute you so that you can ask questions directly in person. There's a few questions here, Josh. I'll read them out. Rohan asks, what specific features is the network looking for in the rocks to utilize the ChemCam on?
Yeah, good question. At the risk of misspeaking again, I'll refer you to the papers, but from my understanding, some of the technology that was built to support that project includes texture information, stratification, shape, size. I think that's mostly it. But I think from what I can remember in talking to people, the texture and the stratification information is pretty important.
There's a question, Maimuna asked, what do you mean when you say you're using AI? Can you speak to what kind of algorithms you're using? I suppose you alluded to it throughout the talk, but maybe if we can
I think
expand on that a little bit.
It's difficult to say in specific. I think that we use a broad class of optimization problems, not necessarily AI. Like when I think of an AI algorithm, I think of like tree search or game theoretic things or stuff like that. A lot of this is just constraint satisfaction on a very large scale or highly constrained optimization. We do sometimes use integer linear programs to understand solutions or to generate them. We sometimes use something called squeaky wheel optimization, which is a way of iteratively generating a plan to work around constraints. and so on. So anything is game. Part of the work, part of the difficulty of being a member of the AI group is actually building up and then drawing from a large pool chest of different algorithms that can be used. So I can't say specifically because it's a very large variety.
So in the ICE node multi-agent concept that you talked about, were the drifters coordinating with each other? And sort of what's the decision making, or where is the decision making happening? Is it on board each vehicle? Is it a centralized concept with a centralized system? So
right. So we would take the ConOps there is we would take the models for the season and yearly variation of the currents. We would run a large process, very expensive process, to solve the Markov decision process and output the policies. The policies would be uploaded onto the individual agents, and then there'd be no further communication or coordination. They would just do their best to execute those policies based on where they are in the world, where they ended up based on these uncertain transitions from the choosing a depth and following a current. The position information is available to them because we have these moored sound sources, which are emitting pings, and so you can trilinearate or triangulate where you are in the world based on that. So what they do is they take in their estimated position, look up what depth they should be at for that given position in the current time, move to that depth, wait a little bit, and repeat that process. And surprisingly, that seems to work as long as you model the currents well enough.
Okay, that's pretty cool. Question, how much reliance is there on data-driven approaches, and how reliable or robust are those?
Space is a data-thin area. If we had a lot of data about a place, we would not go there as much. There are exceptions. So a lot of the Earth missions, we can start to do data-driven approaches for processing what the sensors are observing. I think that's a pretty good regime to do data-driven things. Data-driven decision-making is less utilized, I think.
Okay. Yeah, I think that's which makes it sort of very, very interesting, or interesting for researchers, I suppose. Guess this is a question in response to your last slide. Are there any employment opportunities available at JPL for non-US citizens?
There are actually. So it's not, JPL is not a US person only place. Once you get into JPL, the type of projects that you work on is limited by whether you are a US person and further limited by your classification level or other factors. But it is not at all uncommon to work with foreign nationals at JPL.
Awesome. So that clearly says you did a very good job of talking about making people excited about working in JPL, which is always great. It's a question about data. Sort of is the data available? I suppose this is more broadly speaking for some of the simulations that you mentioned. Are these data sets available for folks to use, researchers or students to use, for example?
Yeah. I think that it is uncommon to find the spacecraft subsystem data available. It is very easy to find the science observations, and that's because that's our job, right, is to bring science data to the world. So you can find all of the observations, the imagery. You can also look up, as far as I understand, the ephemeris, which is the position over time around the planets. So if you wanted to do a study like I did, where we're planning out the position over time and simulating events happening underneath it and actually running classifiers on real imagery of those events, I think that's pretty easy to do. We didn't have a lot of trouble getting that data from public sources. We didn't have to root around inside JPL to get it.
Awesome. All right, last call for questions. These are all great. Anyone else has questions? If you want, I can unmute you. Right, looks like that's it. So again, thanks a lot, Josh. This was a very, very interesting talk. And I bet a lot of people are very excited about all the things that you're doing at JPL. So again, thank you to Lockheed Martin for sponsoring the seminar series. Folks, we have more seminars coming up in the upcoming weeks, so make sure that you register to attend them. And this talk is recorded and will be uploaded on the MRC YouTube channel soon. So you should expect to see it show up on the channel in the next few days. That, thank you very much and have a good weekend.
Thanks, everybody.